Hi gentlemen. Today we're going to focus on stoichiometry. So we're going to begin basically the topic that's going to propel us through the rest of the year. The rest of the course kind of builds on what we're going to do today. Specifically today we're going to talk about stoichiometry when one reactant is in excess. So stoichiometry is basically just the study of predicting or even knowing the amount of product that should be produced in a reaction, given that we know the amounts of the reactants, so the two things that are reacting in a chemical reaction. Okay? So if you can think of a chemical reaction, something like HCl plus NaOH producing H2O and NaCl. Okay, a simple neutralization reaction. Think of this as making a sandwich, okay, where you need, a couple pieces of bread, right, and a couple pieces of bologna to give you a couple sandwiches, right? So it looks like a mushroom. Anyway, apologize for my art. So you end up with your sandwich. The important part of all of this is that we can predict how many sandwiches we can make as long as we know how many pieces of bread we have and how many pieces of bologna. Now, in a chemical reaction like the ones we're going to talk about today, we can actually assume that we have a whole loaf of bread, but only a few pieces of bologna. And so in a case like this, it's very easy to use our pieces of bologna to predict how many sandwiches we can make. If we use 2 pieces of bologna for every sandwich, and we have a whole loaf of bread, but only 2 pieces of bologna, it limits us to 1 sandwich. And that's the type of reactions that we're going to be dealing with today. If we only have, say, 2 molecules of NaOH, all right, we only have 2 of them, and we have 20 of hydrochloric acid, we can only make 2 of our products. And then we have 18 of these left over. And that's fine, right? We don't have to use all these. We can't use them. We don't have anything else over here to use them against. So we call this a limiting reagent. And in our next lesson, we're going to talk about how we figure out which of our reactants limits how many products we can have. Today, though, we are going to assume, and we're going to give you the number, the amount that we have of the limiting reagent. We'll just tell you that this is the other one's in excess. Okay, so you have all the information that you need. So in doing this type of reaction, we need to be able to write a balanced chemical equation, okay, convert the known mass of the reactant or product to an amount in moles, use the balanced chemical equation to determine the ratio of products we have compared to our reactants. So we need to know, based on the number of molecules or the mass that we're given, we need to convert that into moles. Then use the balanced mole ratios to determine how many moles of your product you have in comparison to your reactants. And then you can take that moles of your product and calculate the mass of your final products. So let's look at this equation, this reaction below. Okay? So you have solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. So we have some clues about what the reaction is going to be. We have solid liquid hydroxide removing carbon dioxide. So these must be our reactants. Lithium hydroxide solid plus CO2 must be a gas producing lithium carbonate solid and liquid water. Okay, now we need to balance this. Got 2 here, and I have 4 and 4. 2 and 2. So now I have a nice balanced equation. So my ratio, if you just bring the numbers that were in front down, I have two lithium hydroxides for every one of every other compound. So this is important information because this tells you how much more of the lithium you have than everything else. And we can use that now to determine how much of everything else we're going to produce. And I'll show you how that works in a second. So the question asked, what mass of gaseous carbon dioxide can be absorbed? So I'm actually finding out how much of this I can use up from 1 kilogram of lithium hydroxide. So in this case, we're not even determining a product. Normally you would determine a product, but it works the same way. Today we're going to determine how much of the reactant we use up from 1 kilogram of lithium hydroxide. So I have a mass here. I'm going to put my masses here and my moles here. So I have a mass of 1 kilogram of lithium hydroxide, which we know is 1,000 grams. Now all we have to do is use our M&M equation. So to find our moles. So we cover up our N, we get M over big M, 1,000 grams, and lithium, 7, so 6.49, sorry, 9.4 per mole, plus our 16, plus our 1.01. We get 23.95 grams per mole. So now we can just calculate that. We get 41.7. Let's keep as many decimal places as we can. I'm going to keep 3 decimal places. So this is how many moles I have. So I'm going to put this up here. Great. Now, this tells me I have twice as much lithium as I do carbon dioxide. I think there's 2 times as much lithium hydroxide as carbon dioxide. So when I go across here, I need to divide by the column that I'm in and multiply by the number that I'm going to. Actually, dividing here, you're going from a 2 to a 1. If you're going from a 1 to a 2, you would just multiply by 2. If you're going from a 2 to a 3, you would divide by 2 and multiply by 3 because you try to get that ratio of 3 over 2. Okay. So I'm just going to take my 41.537 and divide by 2. And I get 20.877 moles. So this is my number of moles of carbon dioxide, and now I just need to figure out my mass. So here I divided by the molar mass here. Now I need to determine my mass of carbon dioxide. So I'm going to use my M&M formula again, and now I'm calculating the mass. So I just need N times big M. I'm just going to multiply by big M this time. Take my 20.877 moles, times that by my molar mass here of CO2, which is 12.01 plus 32. 1 carbon is 12.01 grams per mole. 2 times 16 is my 32 grams per mole. So I end up with 44.1 grams per mole for carbon dioxide. So I'm just going to take my 20, multiply by 44.01, and I'm left with 918.79 grams. So I should put this into my formula, shouldn't I? Okay, so now this is my mass. I had 3 significant digits in my question, so I must have 3 significant digits in my answer. So I have 919 grams of carbon dioxide used up when I reacted with 1,000 grams of lithium hydroxide. Okay, so to answer your verso question now, I want you to try example 2. Iron is the most widely used metal in North America, produced by the reaction of iron trioxide with carbon monoxide. So these are your reactants, which produces iron metal and carbon dioxide. So these are now your products. What mass of iron oxide is required to produce 100 grams of iron? So now in this case, we're just working backwards. It works the same way. You start with 100 grams of your iron on the product side and work towards finding how much of your reactant is needed to produce that much. Okay, so try that out. Put your answer in for verso as the answer to that question to check. Thanks, guys.